In this video, we're going to introduce a new way of measuring angles called radian measure. In the past, you've probably used degrees to measure angles, so this will be a new method. Let's start by considering a circle, and let's say that we don't know the length of the radius of the circle, so we're just going to call it radius r. The first thing we can ask is what's the circumference of the circle in terms of r? And this is really just asking for our familiar formula for the circumference of a circle, and we know that the circumference of a circle is equal to 2 pi times the radius. Another way of asking the same thing would be if we were to take a length of string, r units in length, and use it to measure out that circumference. So we take a piece of string that's this long, the length of the radius, and we use it to measure out the circumference. How many pieces of string would it take before we got all the way around the circle? And because the circumference is 2 pi times the length of the radius, that means that it will take exactly 2 pi strings, each of which has the same length as the radius, to get all the way around the circle, for example, from A back to A. If we think along the same lines, we can talk about getting parts of the way around the circle. An arc is a portion of the circumference of the circle. So for example, the arc AB is this part of the circumference of the circle here, this curve. And we can ask how many radius lengths would fit in the arc AC, this half of the circumference of the circle. Well, if it took 2 pi radii to get all the way around, then to get halfway around would be 2 pi over 2, or pi radii. Again, we can imagine that we're taking a string that's the same length as the radius and lying successive strings around the circumference. It would take pi strings to get from A to C. If we wanted to go half that distance, an arc from A to B would therefore take pi over 2 strings of the same length as the radius. And if we wanted to get from A to D, we could work out then that would be 3 pi over 2 radius lengths, or 3 pi over 2 strings, the same length as the radius. And importantly, this isn't going to change if the circle gets bigger or smaller. It's still going to take the same number of strings to get from A to B, for example, or A to C, because as the circle gets bigger, the radius and therefore the strings would get bigger as well. And the same thing if it gets smaller. Now, the measure of an angle in radians, this new unit, is simply the number of radii that you would need to lie end to end to cover the corresponding arc on a circle. What does that mean? It means that the measure of an angle in radians is just the number of string lengths that we've been talking about. How many string lengths does it take to get that length of the arc around the circle, where each string has the same length as the radius? To put that into more concrete terms, angle AC in radians is pi radians, because we said that it's going to take pi strings the same length as the radius to get from A to C. This is exactly the same answer as we just saw. Angle AB is going to take pi over 2 strings the same length as the radius to cover that distance. Therefore, that's pi over 2 radians. And angle AD is going to take 3 pi over 2 strings to cover that whole arc, where each string is the same length as the radius. So these are the same numbers as we saw before, illustrating that radian measure is simply describing how many radius lengths fit in that arc. The word radian comes from radius angle to help remind us that the measure of an angle in radians is simply the number of radius lengths that fit in that arc. We can figure out a formula that relates what we've said above. If theta is the angle in radians, then theta is simply equal to the length of the arc that we're describing divided by the length of the radius for that circle. So theta is equal to A over r, where A is the arc length and r is the radius length. Now you'll notice that both A, the arc length, and r, the radius length, are going to be in the same units, centimeters, meters, etc. Because they're both lengths, when we divide one by the other, those dimensions, centimeters, meters, etc., are going to cancel, and therefore theta is going to be dimensionless. So radians are just a pure number ratio, and that again tells us how many radii fit in the given arc. Let's do a couple of examples now. Here we're given a circle with a radius of 8 centimeters, and we're told that the arc AB is 5.6 centimeters, and we're asked to find theta, the angle here. So recalling that theta in radians is just the number of radius lengths of 8 centimeters that would fit in this arc. Theta is simply equal to 5.6 centimeters divided by 8 centimeters. Again, A over R. And that division gives us 0.7 radians. And because radians is dimensionless, we don't actually have to write anything here. Sometimes you'll see the word or the abbreviation rads written to indicate that it's radians, but if there's nothing written, it means radians as well. So this angle here is 0.7 radians. Doing the same thing on this example, here we're given a circle of radius 8 centimeters again, but this time the arc is 16 centimeters. So figuring out how many radius lengths go in that arc of 16 centimeters is simply dividing 16 by 8, A divided by R, and that's going to give us 2 radians. And again, we don't need to write anything after the 2 because radians are dimensionless. We can also be given questions like this, where we're being asked to solve for the arc length. Here, theta, the angle, is 2.5 radians, and the radius is again 8 centimeters. We know that our formula gives us theta is equal to A over R. Now, this time, we want to solve for A, so we're going to rearrange. By multiplying both sides by R, we get R theta is equal to A. R in this case is 8 centimeters. Theta is 2.5 radians. And multiplying those out, we get 20. In this case, we do need to write the units. 20 centimeters is equal to A, and that's going to be the length of that arc. We also need to know how to convert between degrees and radians. As we saw in the example with the circles above, 2 pi radians, getting all the way around the circle, is equivalent to an angle of 360 degrees. And pi radians, getting halfway around the circle, is equivalent to an angle of 180 degrees. So therefore, because pi radians is equal to 180 degrees, pi over 180, or 180 over pi, can be used as a conversion factor where each is essentially equal to 1, because pi radians is equal to 180 degrees. Multiplying by pi over 180 or multiplying by 180 over pi is not going to change the size of the angle, it's just going to change the units that we're working in. To look at an example, we're asked to express 7 pi over 6 radians in degrees. Now, we can recognize that this is in radians because there's a pi in the expression. Also, if it doesn't have a degree sign or any other measure of a unit, then we know we must be in radians. So we've got 7 pi over 6, and we want to convert it from radians into degrees. We need to multiply by either pi over 180 or 180 over pi, each of which is equivalent to 1, to change the units. And because we want to go from radians to degrees, we need to have the 180 degrees in the numerator. This is a lot like the kind of conversions that you might do in chemistry when you're working and getting things from grams to moles or vice versa. We know that our answer has to be in degrees, so we need degrees in the numerator of our conversion factor. Now we simply cancel out to put things in lowest terms, so pi and pi cancel. 6 goes into 180 30 times, so that's going to become 30 degrees, and that becomes 1. Now all we're left with is 7 times 30 degrees, which is 210 degrees. So 7 pi over 6 radians is equal to 210 degrees, and we got there by multiplying by 180 over pi, because we wanted to convert from radians to degrees. Therefore, we wanted degrees in the numerator. Going in the opposite direction, we can ask, how do we express 135 degrees in radians? Now we have 135 degrees, and this time, because we want our answer to be in radians, radians will be in the numerator of our conversion factor. Again, though, we're using pi over 180, whereas before we used 180 over pi. Each of these is equivalent to 1, because we're getting halfway around the circle. Going pi radians, or 180 degrees, is the same thing. So in this case now we're going to, again, put in lowest terms. So the greatest common factor of 180 and 135 is 45. That's going to go into 180 4 times, go into 135 3 times, and now when we multiply across, we get 3 pi over 4. So 135 degrees is equal to 3 pi over 4 radians. And if you couldn't see that immediately, you could cancel things out bit at a time until you got down to 3 and 4. The more you practice with these, the quicker and more adept you'll become at them. One thing that's helpful is to memorize some of the most frequent angles that you encounter. So, for example, pi over 6, because pi is equal to 180 degrees, is going to be equal to 180 divided by 6, or 30 degrees. Pi over 4 radians 180 divided by 4 is going to be equal to 45 degrees. Pi over 3 radians is 180 degrees divided by 3. That's 60 degrees. So these are our special triangle angles, and they're going to be helpful to recognize. If we took an approach like this to this question, our first question, for example, we could have thought of 7 pi over 6 as 7 times pi over 6, broken it up in that fashion, and then converted pi over 6 to 30 degrees, which is, when we multiply 7 by 30, we get 210. So that's another way that you can do these questions, by memorizing or at least becoming quite familiar with some of the special triangle angles. Others which are helpful to know and which we've seen already is that pi over 2 radians is equal to 90 degrees, pi radians is equal to 180 degrees, 3 pi over 2 radians is 270 degrees, and 2 pi radians going all the way around the circle is equal to 360 degrees. So that's an introduction to radian measure.